Hi everyone. I gave this talk at GopherCon Australia a few weeks ago, but there were some AV challenges that hurt the recording, so I re-recorded this version at home. Enjoy!
This talk is about writing good tests. But first, let's think about why we write tests at all. Why do programmers write tests?
Books about programming say that tests are about finding bugs in your program. For example, this book says that testing is a determined, systematic attempt to break a program that you think is working. And this is true. This is why programmers should write tests. But for most of us here today, it's not why we write tests, because we are not mere programmers. We are software engineers. Let me tell you what I mean. I like to say that software engineering is what happens to programming when you add time and other programmers. Programming means getting a program working. You have a problem to solve, you write some code, you run it, you test it, you debug it, you get your answer, and you're done. That's already pretty difficult, and testing is an important part of that process. But software engineering means doing all that in programs you keep working on for a long time and with other people, and that changes the nature of testing. Let's start by looking at tests for a binary search function. This function find takes a sorted slice, a target value, and a comparison function, and it uses binary search to find and return two things. First, the index where the target would appear if it were present, and second, a Boolean saying whether the target is present. Now, most binary searches are buggy, and this one is no exception, so let's test it. Here's a nice interactive tester for a binary search function. You type two numbers, n and t, it makes a slice of n elements containing increasing multiples of 10, and then it does a search for t in the slice and prints the results, and you repeat. Now, this may seem trivial, but how many of you have ever tested production code just by running it and poking at it for a while? All of us have done that. When you're programming, an interactive tester like this can be very useful for finding bugs, although so far the code appears to be working. But this tester is only good for programming. If you're doing software engineering, meaning you're keeping the program running over a long time and working with other people, this kind of tester is not too useful. You need something that can be run by everyone else every day while they're working on the code, and that can be run automatically by a computer for every commit. The problem is that testing your program by hand only makes sure that it works today. Automated continuous testing makes sure that it keeps working tomorrow and into the future, even if other people who don't know the code as well start working on it. And to be clear, that person who doesn't know the code very well might be you 6 months or even 6 weeks from now. Here's a software engineer's test. You can run it without any knowledge of what the code should do. Any colleague or any computer can run this using GoTest and immediately understand whether the test passes. You've seen tests like this already, I'm sure. The software engineering ideal is to have tests that catch every possible mistake that might be made later. If your tests meet that ideal, then you should be comfortable shipping your code to production automatically anytime your tests are all passing, what people call continuous deployment. If you don't do this already, if the idea of it makes you nervous, it's worth asking yourself why. Either your tests are good enough or they're not. If they are good enough, then why not do it? And if they're not good enough, listen to those doubts and figure out what they're telling you about which tests are missing. A few years back, I was working on the server for the new Go website, go.dev. We deployed the site manually back then, and at least once a week, I would make a change that worked fine on my machine, but then wouldn't serve any pages at all when I deployed it to production. This was annoying and embarrassing. And the solution was better tests and automated continuous deployment. Now, every time a commit lands in the repo, we use a cloud build program to run local tests, push the code out to a fresh server, run a few more tests that only run in production, and then if all is well, redirect traffic to the new server. This made things better in two different ways. First, I stopped causing embarrassing website outages. And second, everyone stopped having to think about deploying the website at all. If they want to make a change, such as fixing a typo or adding a new blog post, they just mail the change. It gets reviewed, it gets tested and submitted, and the automatic process does the rest. To be confident that your program won't break when other people edit it, and to be confident that your program can be pushed to production any time the tests are passing, you need a very good set of tests. But what makes tests good? In general, what makes test code good is the same thing that makes non-test code good: hard work, attention, and time. I don't have any silver bullets or hard rules for writing good test code, any more than I do for writing good non-test code. However, I do have a collection of tips based on what has worked well for us on Go, and I'll share 20 tips in this talk. Tip number 1, make it easy to add new test cases. This is the most important tip, because if it's not easy to add new test cases, you won't. Go already helps with this. This is the most trivial test of the function foo. We designed Go tests specifically to be very easy to write. There's no bookkeeping or ceremony that gets in your way. At the level of package testing, this is pretty good, but in a specific package, you can do even better. I'm sure you know about table-driven tests. We encourage table-driven tests because they make it very easy to add new test cases. Here's the one we saw before. Let's suppose we have only this one test case and we think of a new case to test. We don't have to write any new code at all, just one new line of data. If the goal is make it easy to add new tests, then for simple functions like this, adding a line to a table is about as good as it gets. It does raise one question though. What cases should we add? That takes us to the next tip. Tip number 2, use test coverage to find untested code. After all, tests can't catch bugs in code they don't run. Go ships with built-in support for test coverage. And here's what it looks like. You run go test minus cover profile to write a coverage profile, and then you run go tool cover to view it in your browser. In the display, we can see that our test case is not very good. The actual binary search code is red, meaning entirely untested. The next step is to look at the untested code and think about what kinds of tests would cause those lines to run. On closer examination, we only tested with an empty slice, so let's add a case with a slice that isn't empty. Now we can run the coverage again. This time I'm going to read the coverage profile with a little command line program I wrote called uncover. Uncover prints the lines of code not covered by a test. It doesn't give you the big picture that the web view does, but it lets you stay in a shell window. Uncover shows us that there's just one line left that isn't executed by the tests. It's the line that moves into the second half of the slice, which makes sense since our target is the very first element. Let's add one more test, searching for that last element. When we run the test, it passes, and now we have 100% coverage. Great, are we done? No, and that takes us to the next tip. Tip number 3, coverage is no substitute for thought. Coverage is very useful for pointing out parts of your code that you might have forgotten about, but mechanical tools are no substitute for actually thinking about what the difficult inputs are and what's subtle in your code and how it might break. Code with 100% testing coverage can still have bugs, and this code does. This tip also applies to fuzzing, which is coverage driven, and fuzzing is just trying to explore more and more paths through your code to increase the coverage. Fuzzing is really helpful too, but fuzzing is also no substitute for thought. So what's missing here? One thing to notice is that the only test case that doesn't find the target has an empty input slice. We should check not finding the target in a slice with values. And specifically, we should check what happens when the target is less than all the values, greater than all the values, and in the middle of the values. So let's add 3 more test cases. Notice how easy it is for us to add a new test case. If you think of a case that your code might not handle correctly, it needs to be as easy as possible to add that case, or you will be tempted not to bother. If it's too difficult, you won't. You can also see how we're starting to enumerate all the important ways that this function can go wrong. The tests constrain all future development to keep the binary search working at least this well. When we run these tests, they fail. The returned index I is correct, but the Boolean indicating whether the target was found is wrong. So let's look at that. Reading the code, the Boolean expression at the return statement is wrong. It was only checking that the index is in range. It also needs to check that the value at that index equals the target. So we can make that change, highlighted here, and now the tests pass. Now we feel pretty good about the test. Coverage is happy and we've thought hard about it. What more can we do? Tip number 4, write exhaustive tests. If you can test every possible input to a function, you should. Now that may be unrealistic, but you can usually test all inputs up to a certain size under certain constraints. Here's an exhaustive test for binary search. We start by making a slice of 10 elements, specifically the odd numbers 1, 3, 5 up to 19. Then we consider all possible length prefixes of that slice. And for each prefix, we consider all possible targets from 0, which is smaller than all the values in the slice, up to twice the length, which is larger than all the values in the slice. This will exhaustively test every possible search path through every possible size slice up to our length 10 limit. But now, how do we know what the answer is? We could do some math based on the specifics of our test case, but there's a better, more general way. That way is to write a reference implementation that is different from the real one. Ideally, the reference implementation should be obviously correct, but it can just be any different approach from the real one. Usually, that will be a simpler, slower approach, since if it was simpler and faster, you'd use it as the real implementation. In this case, the reference implementation is called slow find. The test checks that slow find and find agree on the answer. Since the inputs are small, slow find can be a simple linear search. This pattern of generating all possible inputs up to some size and comparing the results against a simple reference implementation is very powerful. One important thing it does is cover all the basic corner cases, like 0-element slices, 1-element slices, slices that have odd length, even length, power of 2 length, and so on. The vast majority of bugs in most programs can be reproduced by small inputs, so testing all the small inputs is very effective. It turns out that this exhaustive test passes. Our thinking was pretty good. Now, if the exhaustive test fails, that means find and slow find disagree. So at least one is buggy, but we don't know which one. It helps to add a direct test of slow find, and that's easy since we already have a table of test data. This is another benefit of table-driven tests. The tables can be used to test more than one implementation. So tip number 5, separate test cases from test logic. In a table-driven test, the cases are in the table, and the loop that processes them is the test logic. As we just saw, separating those lets you use the same test cases in multiple contexts. So now are we done with binary search? It turns out no, there is still a bug left. Which leads us to tip number 6, look for special cases. Even if we've done an exhaustive test of all the small cases, there may still be bugs lurking. Now here's the code again. There's one bug left. You can pause the video and look at it for a while. Does anyone see it? It's okay if you don't see it. It's a very special case, and it took people decades to notice. Knuth told us that although binary search was published in 1946, the first correct binary search wasn't published until 1964. But this bug wasn't discovered until 2006. The bug is that if the number of elements in the slice is very close to the maximum value for an int, then I plus j overflows. So then I plus j over 2 is the wrong calculation for the middle of the slice. This bug was discovered back in 2006 in C programs using 64-bit memories and 32-bit ints, indexing arrays with more than 1 billion entries. This particular combination is basically never going to happen in Go, because we require that 64-bit memories use 64-bit ints, exactly to avoid this kind of problem. But since we know about the bug, and you never know how you or someone else will adapt the code in the future, it's worth avoiding it. There are 2 standard fixes to keep the math from overflowing. The slightly faster one is to do an unsigned divide. So suppose we fix that. Now are we done? No, because we haven't written a test. Tip number 7. If you didn't add a test, you didn't fix the bug. This is true in 2 different ways. The first way is the programming way. If you didn't test it, the bug might not even be fixed. This may sound silly, but how often has this happened to you? Someone tells you about a bug, you know immediately what the fix is, you make the change, you tell them it's fixed, and they come right back and say, nope, it's still broken. Writing the test saves you that embarrassment. You can say, well, I'm sorry I didn't fix your bug, but I did fix a bug. And I'll take a look at this one again. The second way this is true is the software engineering way, the time and other programmers way. Bugs are not random. In any given program, certain mistakes are far more likely than others. So if you made the mistake once, you or someone else will probably make it again in the future. Without a test to stop them, the bugs come back. Now this specific test is hard to write because the input has to be very large. But this tip is true even when the test is hard to write. In fact, it's usually more true in that case. To test this case, one possibility would be to write a test that only runs on 32-bit systems and that does a binary search over 2 gigabytes of uint8s. But that's a lot of memory, and we don't have many 32-bit systems anymore. There is a more clever answer in this case, as there often is for testing hard-to-find bugs. We can make a slice of empty structs, which takes up no memory, no matter how long it is. So then this test calls find on a slice of maxint empty structs, looking for an empty struct as a target, but then it passes in a comparison function that always returns -1, claiming that the slice element is less than the target. This will make binary search investigate larger and larger indexes into the slice, which is how we can reach the overflow. So if we revert our fix and run this test, sure enough, the test fails. And with our fix, the test passes. So now the bug is fixed. Tip number 8, not everything fits in a table. This special case didn't, and that's okay. But lots of things do fit in a table. Here's one of my favorite test tables. This is from the fump.printf tests. Each row is a printf format, a value, and the expected string. The real table is far too large to fit on a slide, but here are a few lines from it. If you read through the table, you start to see what are clearly bug fixes. Remember tip number 7, if you didn't add a test, you didn't fix the bug. The table made each of these tests trivial to add, and adding them makes sure these bugs never come back. Now, tables are one way to separate test cases from test logic and make it easy to add new test cases. But sometimes you have so many tests that it makes sense to avoid even the overhead of writing Go syntax. For example, here's a test file from package strconv for testing conversion between strings and floating point numbers. You might think that it's too much work to write a parser for this input, but once you know how, it's not much work, and being able to define testing mini-languages turns out to be incredibly useful. So I'm going to walk quickly through the parser to show that there's not much to it. We read the file, then we split it into lines. For each line, we calculate the line number for error messages. Slice element 0 is line 1. We cut off any comments from the end of the line, and if the line is blank, we skip it. This is pretty standard boilerplate so far, so now the good part. We split the line into fields, and we pull out the 4 fields. Then we do the conversion in float32 or float64 math, according to the type field. My A to F64 is basically strconv.parsefloat64, except it handles a decimal P format that lets us write the test cases the way they were written in the paper I copied them from. Finally, if the result is not what we want, we print the error. This is a lot like a table-driven test. We just parse the file instead of ranging over a table. It doesn't fit on one slide, but it does fit on one screen when you're developing. Tip number 9. Test cases can be in test data files. They don't have to be in your source code. As another example, the Go regular expression package includes some test data files copied from the AT&T POSIX regular expression library. I won't go into the details here, but I'm grateful that they chose to use a file-driven test for that library, because it meant I could reuse the test data files for Go. It's another ad hoc format, but it's easily parsed and easily edited. Tip number 10, compare against other implementations. Comparing against the AT&T regex test cases help make sure that Go's package handled various corner cases exactly the same way. We also compare Go's package against the C++ RE2 library. To avoid needing to compile the C++ code, we run it in a mode that logs all its test cases to a file, and then we check in that file in Go as test data. Another way to store test cases in files is to have pairs of files, one for input and one for output. To implement gotest-json, there's a program called test2json that reads test output and converts it to JSON output. The test data is pairs of files, test output and JSON output. Here's the shortest file. The test output is at the top, and that's the input to test2json, and that should produce the JSON output at the bottom. Here's the implementation to show the idioms for reading test data from files. We start by using filepath.glob to find all the test data. If that fails or doesn't find any, we complain. Otherwise, we loop over all the files. For each one, we create a subtest name by taking the base file name without the test data /directory name and without the file suffix. Then we run a subtest with that name. If your test cases are complex enough to have one per file, it almost always makes sense to make each one its own subtest. That way, when one is failing, you can run just that specific file using gotest-run. For the actual test case, we just have to read the file, run the converter, and then check whether the results match. For the check, I started out using bytes.equal, but over time it became worthwhile to write a custom diff.json that parses the two JSON results and prints a nice explanation of what's actually different. Tip number 11, make test failures readable. Rewinding a bit, we've already seen this with binary search. I think we all agree that the pink box is not a good failure. But there are two details in the yellow box that make these failures especially good. First, we check both return values in a single if statement, and then we print the full input and output in a concise single line. Second, we don't stop at the first failure. We call t.error instead of t.fatal to let more cases run. Combined, these two choices let us see the full details of each failure and look for patterns across multiple failures. Moving back to test2JSON, here is how its test fails. It calculates which events are different and marks them clearly. One important point is that you don't have to write this kind of sophisticated code when you first write the test. Bytes.equal was fine to get going and focus on the code. But as the failures become more subtle and you notice yourself spending too much time just reading the failure output, that's a good signal to spend some time on making them more readable. Also, these kinds of tests can be a bit annoying to update if the exact output changes and you need to correct all the test data files. So tip number 12, if the answers can change, write code to update them. The usual way to do this is to add a -update flag to the test. Here's the updating code for test2JSON. The test defines a new flag -update. When the flag is true, the test writes the computed answer to the answer file instead of calling diff.json. Now, when we make an intentional change to the JSON format, goTest -update corrects all the answers. You can also use version control tools like gitdiff to review the changes and back them out if they don't look right. Staying on the topic of test files, sometimes it's annoying to have a test case split across multiple files. If I was writing this test today, I wouldn't do that. Tip number 13, use TextR for multi-file test cases. TextR is a new archive format we designed a few years ago, specifically to solve the multi-file test case problem. The Go parser is in Golang.org's xtools TextR, and I've also found parsers written in Ruby, Rust, and Swift. TextR's design had 3 goals. First, be trivial enough to create, edit, and read by hand. Second, be able to store trees of text files, because we needed that for the Go command. And third, diff nicely in Git history and code reviews. Non-goals included being a completely general archive format, storing binary data, storing file modes, storing special files like symbolic links, and so on. These are non-goals because archive file formats tend toward becoming arbitrarily complex, and complexity directly contradicts the first goals. These goals and non-goals led to a very simple format. Here's an example. The TextR file starts with a comment. In this case, here are some greetings. And then in general, there are 0 or more files, each introduced by a line of the form -- space, file name, space -- This archive has 2 one-line files, hello and g'day. That's it. That's the entire format. There's no escaping, no quoting, no support for binary data, no symlinks, no possible syntax errors, and no complications. Here's a real use in test data for a package that computes diffs. In this case, the comment is useful for people to record what's being tested. And then in this test, each case is 2 files followed by their diff. Using TextR files is almost as trivial as writing them. Here's the test for the diff package we were looking at. This is the usual file-based loop, but we call textr.parsefile on the file. Then we insist the archive contain 3 files, the third being named diff. Then we diff the 2 input files and check that the result matches the expected diff. And that's the whole test. You may have noticed the file data is passed to this function clean before being used. Clean lets us add some diff-specific extensions for this test without complicating the TextR format itself. The first extension handles lines ending in spaces, which do happen in diffs. Lots of editors want to remove those trailing spaces, so the test allows placing a $sign at the end of a TextR data line to mark the ending, and then clean removes that $sign. In this example, the marked lines need to end in a single space. Also, TextR insists that every line in a file ends in a new line character, but we want to test diff's behavior on files that don't end in a new line. So the test allows a literal $D at the end. Clean removes both the $D and the new line that follows it. In this case, the new file ends up without a final new line, which the diff correctly reports. So even though TextR is incredibly simple, you can layer your own format adjustments on top easily. Of course, it is important to document these so that the people who work on the test next understand them. Tip number 14, annotate existing formats to create testing mini-languages. Annotating an existing format, like adding the $sign and $D to TextR, is a powerful tool. Here's another example of annotating an existing format. This is a test for the Go type checker. This is a plain Go input file, but the expected type errors have been added in /star error comments. We use /star comments so we can place them exactly where the error should be reported. The test runs the type checker and then checks that it produces the expected messages at the expected locations and does not produce any unexpected messages. Here's another example from the type checker. In this test, we've added an assert annotation on top of the usual Go syntax. This lets us write tests of constant arithmetic, like this one. The type checker is already computing the Boolean value of each of those constant expressions, so checking the assert is really just checking that the constant has evaluated to true. Here's another example of an annotated format. Ivy is an interactive calculator. You type programs, usually simple expressions, and it prints back the answers. The test cases are files that look like this. The unindented lines are Ivy input, and the indented lines are annotations of what output to expect Ivy to print at that point. It doesn't get much easier to write a new test case than this. These annotated formats are extending existing parsers and printers. But sometimes it helps to write your own parsers and printers from scratch. After all, most tests involve creating or inspecting data, and those tests are always far nicer when you can work with the data in a convenient form. So tip number 15, write parsers and printers to simplify tests. These parsers and printers don't have to be for standalone scripts and test data files. It's also possible to use them in regular Go code. Here's a fragment of a test for the code that runs deps.dev. This test sets up some database table rows. It calls a function that uses the database and is being tested, and then it checks that the database contains the expected results. The insert and want calls are using a mini language for database contents written specifically for these tests. The parser is as easy as it looks. It splits the input into lines and then splits each line into fields. The first line gives the column name. That's it. The exact spacing in these strings doesn't matter, but of course it looks nice if they're all aligned. So to support this test, the deps.dev team also has a code formatter written just for these tests. It uses the Go standard library to parse the test source files, then it walks over the Go syntax tree to look for calls to insert or want. It extracts the string arguments and parses them into tables. Then it reprints the tables back to strings, reinserts the strings back into the syntax tree, and reprints the syntax tree back to Go source code. This is just an extended version of GoFumped, using the same packages that GoFump uses. I won't show it to you, but it's not much code. The parser and printer took some time to write, but now every time someone writes a test, that test is that much easier to write. And every time a test fails or needs updating, it's that much easier to debug. So if you're doing software engineering, the benefits scale with the number of programmers and the lifetime of the project. For deps.dev, already the time spent on this parser and printer has been saved many times over. Perhaps even more importantly, because tests are easier to write, you're likely to write more tests, which results in higher quality code. Tip number 16, code quality is limited by test quality. If you can't write high quality tests, you won't write enough tests, and you won't end up with high quality code. Now I want to show you some of the highest quality tests I've ever worked on, which are the tests for the Go command. These bring together many of the ideas we've seen so far. Here's a simple but real Go command test. This is a TextR input with a single file hello.go. The archive comment is a script written in a simple line-at-a-time command language. In the script, env sets an environment variable to turn off Go modules. A hash sign introduces a comment, and Go runs the Go command, which should in turn run hello world. That program should print hello world to standard error. The stder command checks that the standard error printed by the previous command matches a regular expression. So this test runs go run hello.go and checks that it printed hello world to standard error. Here's another real test. Notice at the bottom that a.go is an invalid program since it's importing an empty string.
The bang at the start of the first line is a not operator. Not go list a.go means go list a.go should fail. The next line, not stood out dot, means that there should be no matches on standard output for the regular expression dot, meaning no text at all should be printed. Next, standard error should have an invalid import path message. And finally, there should not be a panic. Tip number 17, scripts make good tests. These scripts make it incredibly easy to add a new test case. Here's our smallest test, 2 lines. I added this one recently after I broke the error message that gets printed for an unknown command. In all, we have over 700 of these script tests, ranging from 2 lines to over 500 lines. These test scripts replaced a much more traditional test scaffold with methods. This slide shows one of the real tests it replaced behind the script translation. The details don't matter except to notice that the script is much easier to write and to understand. Tip number 18, try rsc.io/script for your own script-based test cases. It's been about 5 years since we created the Go script tests, and we're very happy with the specific script engine. Brian Mills took the time to give it a very nice API, and earlier in November I posted it for import at rsc.io/script. Now I said try because it's a bit new, and ironically it doesn't have enough tests itself since the importable package is only a few weeks old. But you still might find it useful, and we might put it somewhere more official when we have more experience with it. So if you do try it, let me know how it goes. The motivation for extracting the script engine was to reuse it in a different part of the Go command tests. This script is preparing a Git repository containing a module that we want to import during a regular Go command script test. You can see it sets some environment variables, runs an actual Git init, sets the time, runs more Git commands to add a hello world file to the repo, and then checks that we got exactly the repo we wanted. Once again, the test did not start out this way, which leads me to the next tip. Tip number 19, improve your tests over time. Originally, we didn't have these repo scripts. We created small test repos by hand and posted them on GitHub, Bitbucket, and other hosting servers, depending on which version control system we needed. That worked okay, but it meant that if any of these servers went down, the test failed. Eventually, we took the time to build our own cloud server that could serve repos for every version control system. Now we created the repos by hand, zipped them up, and copied them to the server. That was better, since now there was only one server that could take down our tests, but sometimes there were networking problems too. It was also a problem that the test repos themselves were not version controlled, and they were not near the tests that used them. The script-based version builds and serves these repos entirely locally as part of the test, and now the repo descriptions are easy to find, change, and review. This is a lot of infrastructure, but it's testing a lot of code too. If you have only 10 lines of code, you should not have thousands of lines of test framework. But if you have 100,000 lines of code, which is about what the Go command is, then a few thousand lines to make tests better, or even 10,000 lines, is almost certainly a good investment. Tip number 20, aim for continuous deployment. There may be policy reasons that you can't actually deploy your code on every commit that passes all the tests, but aim for it anyway. As I mentioned at the start of the talk, any doubts you have about continuous deployment are helpful little voices telling you what needs better testing. And the key to better testing is, of course, to make it easy to add new tests. Even if you never actually enable continuous deployment, aiming for it can help keep you honest, improve the quality of your tests, and improve the quality of your code. I mentioned earlier that the Go website uses continuous deployment. On each commit, we run tests to decide whether the latest version of the code can be deployed and have traffic routed to it. At this point, you won't be surprised that we wrote a testing script language for these tests. Here's what they look like. Each test begins with an HTTP request. Here, we get the main go.dev page. Then there are assertions about the response. Each assertion is of the form field operator value. Here, the field is body, the operator is contains, and the value is literal text that the body must contain. This test is checking that the page is rendering, so it checks for basic text as well as a subheading. To make it easier to write the tests, there's no quoting at all. The value is just the rest of the line after the operator. Here's another test case. For historical reasons, /about needs to redirect to package.go.dev. Here's another. Nothing special here, just checking that the case studies page renders, because it's synthesized from many other files. Another field the test can check is the HTTP response code. And here's a bug fix. We were accidentally serving these files from the Go repo root as if they were Go website pages. We want 404s for these instead. Another field you can test is header foo for some foo. In this case, the header content type needs to be set correctly for the main blog page and its JSON feed. Here's another example. This one uses the regular expression matching operator tilde and the \s+ syntax to make sure that the page has the right text no matter how many spaces are between the words. That got a little bit old, so we added a new field named trimBody that is the body with all runs of spaces replaced by a single space. This example also shows that the value can be supplied as multiple indented lines to make multi-line matches easier. We also have some tests that can't be run locally, but are still worth running in production before we migrate live traffic to the server. And here are two of these. These depend on network access to the production playground backends. These cases are the same except for the URLs, and this is not a terribly readable test, since these are our only post tests. If we added more of these, at that point I would probably take the time to make them a bit nicer, in the spirit of improve your tests over time. But for now they're fine and they serve an important purpose. Finally, as usual, it's easy to add bug fixes. In issue 51989, certain talks were not rendering at all. So this test checks that the page does render and that it contains a distinctive piece of text. Issue 51989 is never going to happen again, at least not on the live website. There will be other bugs for sure, but that one is gone for good, and that's progress. So that's all the examples I have time to show you. But one final thought. I'm sure you've had the experience of chasing down a bug and ending up in an important piece of code that's wrong. But somehow, it's wrong in a way that doesn't matter most of the time, or wrong in a way that's canceled out by some other wrong piece of code. And you probably thought to yourself, how did this code ever work? If you wrote the code, you might have thought you got lucky. And if someone else wrote the code, you might have thought poorly of them, and then also thought that they got lucky. But most of the time, the answer isn't luck. The answer to how did this code ever work is almost always because it had a test. Sure, the code is wrong, but the test checked that it was correct enough for the rest of the system to work, and that's what mattered. Maybe the person who wrote the code was in fact a bad programmer, but they were a good software engineer because they wrote a test, and that's why the overall system containing that code works. What I hope you take away from this talk is not the specific details of any given test, although I do hope you'll keep an eye out for good uses for small parsers and printers. Anyone can learn how to write those, and using them effectively can be a software engineering superpower. Ultimately, these were good tests for these packages. Good tests for your packages may well look different, and that's fine. But make it easy to add new tests, and make sure that you have good, clear, high-quality tests. Remember that code quality is limited by test quality, so invest in improving your tests gradually over time. The longer you work on a project, the better your tests should become. And aim for continuous deployment, at least as a thought experiment to understand what's not tested well enough. Overall, put as much thought and care and effort into writing good test code as you do into writing good non-test code. It's absolutely worth it.